new modalities that connect various domains, as well as constructing personal co-pilots, as well as assistants for the digital as well as physical world. So without further ado, I will let Xin share her very recent amazing research insights to the audience. Yeah, stage is yours, Xin.
All right, thank you so much. So yeah, hello everyone. It's too bad, thanks for having me today. It's too bad I couldn't attend the conference in person, but so glad to see you all online. So I'm Xin Wang from Microsoft Research, and today I'm going to talk about data efficient learning, their top-down attention steering in the context of training big vision models. So in the big model era, so there are a lot of opportunities in big vision and language community. So we've seen the power of scaling. So we saw big models trained on larger data sets with longer training skills often leads to better performance and generalization on new downstream tasks. For example, in this figure, we've seen the green curves are the NLP models. So starting from 2018, it may have a couple million parameter models. And today, the size of the model has been grown to thousands of billion parameter models. And also, if you look at the orange curve, it's actually the vision transformer models that's been introduced in 2021. And the size of the model has been grown vastly as well. Recently, the researchers have scaling up vision transformers to 22 billion parameters. So there's a huge desire to train a large vision foundation models, and hopefully that would achieve better generalization and building generalist models on different downstream tasks. Well, this still give us a lot of challenges ahead for training large vision models. So the first thing is the need for high quality data sets. So at the same goals, data is the key. So if you look at the successful story for large language models, so the language models are usually trained on several billions or trillion text tokens, and the high quality data is the key to success. So for example, in the recent paper, textbook are all you need. So the researcher shows that with the high quality textbook level data from generated from GPT-4, you can actually achieve train even smaller language models which is as competitive to big models. So this is all telling us the importance of data. And if you look at the vision community, the size of the data is still relatively small, especially the clean data with human labels. So probably the largest data is at the scale of several million images. It is still way below the size of we will hope for. And the vast majority of the image or video data is noisy and unlabeled. So this has been a core research problem for many of us, how to leverage and utilize the video data that is noisy and unlabeled. So, and another thing I would like to mention is that there's a need for more scalable and efficient representations. So since 2021, the adoption of a transformer architecture in computer vision has started to make this transformer-based model more ubiquitous in different applications. So we've seen that the soft attention-based transformers have shown better generalization and stronger scalability, and it also unifies different communities languages audio, and it's gives us the hope for training a unified model for different applications. And still there's a need for room for more study for scalable and efficient representations, because especially for vision, we've seen the model 22 billion parameter models is not as good as we would hope for a bigger vision foundation models. So there's a lot of room for designing how scalable and efficient representations. So in this talk, I would like to give a brief tutorial about building dynamic representations for data efficient learning in the context of training big vision models. So there's a lot of terms. I promise I will explain the terms in the following slides. So the topics that I would like to cover first is task-aware representations, where like weight prediction. So this enables efficient transfer to new tasks with like few examples. And the next I will talk about top-down attention for video pre-training. So the top-down attention is like new design or attention design, which will allow the network to attend to task-related information, which actually achieves a better performance than self-attention mechanisms. And the same design could be actually used for task time adaptation as well, which like allows the model to steering the attentions at task time for efficient transfer to new tasks and new data sets. So let's first dive into the first one. So how to build like a task-aware feature representation. And before that, I would like to give you some like definition of what is like dynamic neural networks. So this is a definition I cited from a survey paper, dynamic neural networks paper. The link is on the slide. So it says like the dynamic neural networks are the ones they can adapt their structures or parameters to different inputs, leading to notable advantages in terms of computation efficiency, adaptiveness, data efficiency, etc. So that is to see like any models that actually adjust their execution paths, structures, parameters to different models are considered different inputs are considered as dynamic neural networks. And one line of the work in this literature is to for the models to have like a dynamic structure. So some notable techniques would be mixture of expert, which the model is composed of like several experts, which is a subnetwork, and then like for each input, the model will choose to execute a subset of the expert. In this way, the model can actually reduce the computational cost while maintaining the expressivity of the model. And you can also do like a dynamic routing. So in this case, you like within a single network, the model can actually adjust this execution path based on the complexity of input. So for example, the easier example will execute fewer layers, and complex models will execute like more layers. So you can similarly to do model cascades to compose like a model level, like models of different complexities to achieve like your target accuracy. So this this type of like dynamic architectures have been widely used in training like large language models and vision models for better computation like efficiency. So well, this is actually not the core topic of this work. I want to give you some background on this line of work. So if you're interested, you can actually refer to the links on the slides for more information. And next, another line of research in dynamic neural network is actually adapting the parameters and features of the model to enable like a low-shot learning for better generalization. So, and I would like to first introduce a work we covered in like 2019, which is constructing a task-aware feature representations for the model. So what is that? So here's the cartoon illustration to show the expected behavior of taffy. So suppose this is the feature embedding space, and the white the gray planes are the decision boundaries, which divide the space into the positive region above and the negative region below. So the first task is to recognize whether the input image is a dog. So you can see like all the dog images are projected to the positive region, while the other images like birds or cats are projected to the negative region. And if we change to a different task, which is to recognize cat, and then we will see the same dog images it's not projected to the negative region, while the cat images is going to be projected to positive region. So this is saying like if you even for the same input, so under different task description, the model will actually adjust its feature representation for the same input. So like just in the few shot learning setting, you will imagine like doing training, you have seen a lot of different task descriptions, and at test time, you would like to generalize to new tasks. You just give the model a new task embedding, and hopefully the model will adjust it to the adjust its feature for the new task. So with that, how do we actually build a model to achieve that? So this is the we propose an architecture called like a TAFINet. So to do this, this network actually composed of like two branches. So which first we have a task-aware meta learner, which will take the input of the task descriptions and pass it to an embedding network to get the task embedding. And based on that, we have a bunch of like parameter generators for different layers of the network to generate parameters of a prediction network, which is on the bottom. So you will see like for each image, instead of goes through a static neural network, you can actually now facing a bunch of the reconfigurable layers on the network, which is the blue boxes. These features, the parameters of these layers are going to be generated by the meta learner. And then like through this like weight generation procedure, you will be able to adapt the network parameters for the different tasks. And to train this model, we first use this like embedding laws to align the task embeddings with the task-aware feature embeddings, and also to have a classification laws to train them all together. So the challenge for this design is how to reduce the cost for generating the parameters, because if you imagine like a convolution layers which is composed like thousands of channels, and then there's going to be very costly to generate those parameters. So what we did was like to do a weight generation through factorization. So the way it works is like we will first decompose the weights into a shared parts, which is the same size as the original weight of the convolution network. And then but it's shared across like all different tasks. And then we have a task-specific weight, which is actually along the output dimension of the convolution layer. And then like the weight of the feature is a group convolution between the shared weights and the task-specific weights. So then in this time, in this way, the model only need to generate a small set of the task-specific weights instead of the full weight vector, so which will reduce the size of the generation complexity. So to do some evaluation on this model, what we did in like back to like 2019 was some like a compositional data sets, like Learning learning data sets, Stanford VRD and MIT State's data sets. So in these data sets, an attribute object pairs forms a class, and the goal is to recognize the unseen combinations at test time. So here we use the word embedding of the attributes and objects as a task description and report the top one classification accuracy on the evaluation set. So here's the plots for the results. So at that time, you can see like TAFINet actually outperforms the previous methods, and it generates better than previous approach on unseen combinations by a large margin. So with this, I hope we this is the one with weight prediction, we can actually adjust the parameters of the network, but still it faces a lot of uncertainties, like how this is going to be reliable if you have like completely new set new training data, and sometimes it could be like unstable to train this type of like models. So what do we do? So the techniques we introduced more recently is based on this like attention mechanism. So you can actually adjust the features for different inputs. And here I'm going to talk about the second work, top-down attention for visual pre-training. So actually, attention is also playing a very important role in human vision systems. So for example, if we look at this picture, like our attention will first land on the eyes, nose, mouth, and then on the hairs and contours. So attention helps the visual system to attract the salient features and process the visual features like more efficiently. So similarly, the neural networks like transformers also adopt the attention as part of the designs. So their attention will showcase the salient regions in the input image, and then like this representation is going to be useful for many downstream applications. So in the high level, this self-attention based method can be categorized as a bottom-up attention. So which is saying like for a given image, this input will driven the feature salient map. So for example, this image, you can see a husky and you can see a cat. So for a bottom-up attention, the model will highlight all the salient regions and all the salient objects. Well, this is actually the self-attention mechanism is part of. It can be categorized to this bottom-up attention. And the one we wanted to talk about is this like top-down attention. So the way it works is first you have this image, and it's also have a high-level task. So for example, if I ask you a question, is the husky looking at the camera? So then you kind of like trigger like find where's like the husky, and you want to put your attention on the husky instead of the cat. So with the top-down attention, so the model will only highlight the objects that's relevant to the current task. So actually, I want to mention this both like top-down attention and bottom-up attention existing in human vision. And the top-down attention will mostly attend to like a task-related information, which needs a high-level goal or high-level prior. And this enables us to the visual system to have a more task-aware representations. And it's kind of like a less studied in the transformer literature. So the work I'm gonna introduce here is called like a top-down visual attention from analysis by synthesis. This is the joint work was like by Feng Shi and Travadero from Berkeley, which was like accepted as a CVPR 2023 paper. In this work, again, we will show like how we wanted to adjust the bottom-up attention without the goal into something like more like a goal-driven like attention design. So like if you're asking, is it husky looking at the camera versus like what's the color of the cat strips? So this will basically steering the attention through high-level tasks and goals. So in the architecture we proposed, it works in like I'll first walk you through the process. So the base network is actually a vision transformer model. So the first thing we would like to do is like, okay, we do a feed-forward pass. First, the feed-forward pass of the input image. So basically, the input image is the pass through the feed-forward backbone, which is like VIT, and then like we'll highlight all the salient objects in the image. And then the next step is we take the task embeddings, and then we would like to use it to reweight the output tokens from the first step. And the token get higher weights if it's more relevant to the current task, and the lower weights if it's less relevant to the task. So this step we will select the task relevant tokens to the relevant tokens to and that is relevant to this task. And the third step, we will send back the reweighted tokens to each self-attention layers. You can see like you have a pathway from the top, and which will basically add it to the self-attention layers in the backbone for each step. And the fourth step, we will basically run the feed-forward path again, but this time each attention layer receives additional top-down inputs, and the top-down input is added on the bottom-up signal for the value matrices. And in this way, we were able to highlight all the like task-relevant objects. So this is the high-level design of the of this like ABS-VIT architecture. And the math behind it is like, or the intuition behind it is actually coming from a classic idea called analysis by synthesis. So basically, the analysis by synthesis hypothesis that our visual perception is a Bayesian inference process, which means like our perception of image does not only depend on the image, but also a high-level prior. So in this work, we kind of like formulate the top-down attention as a Bayesian inference. So like if you change like the high-level task as a we use the high-level task as a prior, which will affect the latent representations and the attention. So compared to a bottom-up attention, which could be formulated as a sparse reconstruction problem. So there's like some details about how we can actually convert self-attention into a sparse reconstruction problem. So the details are actually in this ICML paper. I will probably not talk too much about this in this talk due to this the time limit. And then like if you compared to the bottom-up attention, we can actually add the additional top-down signal in this formulation to reconstruct the input. And then like we will be able to have a top-down attention design. And for learning objectives, so we train this model with two losses to variationally approximate Bayesian inference, which is similar to VAE designs. The first one is the alignment loss. This is to make sure that the output is aligned with the prior or the task description. And the second one is the reconstruction loss on the bottom. So this is to encourage the model, the feedback path to reconstruct the input image from the output tokens. So, and the third one is the task loss. It could be a supervised loss or it could be unsupervised loss, depends on the task. And this all three things are going to be optimized together to train a model. So here, like first, I would like to show you some like visualizations about the top-down attention. Here, what we did is to randomly sample like two images from ImageNet, and we used the class embeddings of each class as the prior, and we observed that the model is able to adjust its attention to different objects when given to different priors. So for example, there's like a woman walking a dog, and if you give the dog classifier like a prior, it will only highlight the lower bottom region, and if you give the sunglasses, it will basically highlight these little regions on the top. And we also compared with other we also compared with like other, give you like more examples and compared with other like methods like perceiver IO and mask attention. So perceiver IO mostly focus on like targets that's a little bit noisy, and the mask attention seems to missing like objects from time to time. But if you look at our method, the ABS-VIT models, we actually give a much cleaner attention map compared to like existing models. And for more evaluations, we also apply this top-down design on visual language tasks like VQA and near-shot image retrieval. So here we actually use the natural language to guide the top-down attention. So it turns out the EBS-VIT models is able to focus its attention on the object that is more relevant to the language inputs. And we also show some like comparison with the human human attention on VQA tasks. And for like some vision only tasks, we evaluate the model on segmentation task on Pascal VOC Cityscape 8020K, and also show some improved robustness on all the images as well. So this is another visualizations on ImageNet data. So we can see like the top-down attention is kind of focused more on like the object and give you a cleaner map. So with this, like we show you like how how this like top-down attention is helpful for you to train a backbone network, like could be considered as a replacement for the standard like VIT model, but it's like a better better performance on a variety of tasks. And next, I would like to show you how this design could be used for generalization to like different downstream tasks, like 4 times time adaptation.
Hi, Xin, can you hear us?
Yes.
So yeah, we have some network problem earlier. So would it be fine if you go back maybe for like 3 minutes or 3 minutes? We lost you for 3 minutes. It's a little bit hard. Yeah, you can
3 minutes.
I can point.
Let me see. Which slides are?
Yeah, can you move backward? Maybe one more.
This one?
Yeah, maybe next one. Yeah, maybe one more. Yeah, I think we're here. Yeah, can you just try to continue from here? Thanks so much. Sorry for.
All right. Yeah. So no problem. So I think for this. All right. So let me walk you through the training losses for this design. So similar to like VE models, we have alignment loss, which is to make sure like the output is aligned with the prior. And we also have this like reconstruction loss that is to encourage the feedback path to reconstruct the input image. And when training this model, we will use the alignment loss, reconstruction loss, plus the task loss, which could be a supervised loss or unsupervised loss altogether to learn this like top-down attention. And we did some visualizations on ImageNet first. So this is like in this one, we randomly sample like 2 images from from ImageNet and use the class embeddings of each class as a prior. And then we can see the model can adjust its attention based on the class priors. So for example, here this one in the dog image class. So the model will only highlight the dog region, which is on the bottom. And even if you give a smaller object like sunglasses, we can actually visualize to see like the sunglasses region are actually highlighted in this ABS VIT model. And more evaluations can be found here. And we also compared with other attention designs like a perceiver IO and mask attention. And this in this like second and third column. So we can see the perceiver IO, the attention map is kind of a bit noisier, and the mask attention sometimes like missing like details about the objects. So the ABS VIT kind of gave like a cleaner like attention maps. And we also did some quantitative evaluations on vision language tasks like VQA and Dearshot image retrieval. So we used the natural language to guide the top-down attention, and the ABS like VIT achieves the consistent improvements on both tasks. And we also do some like visualizations compare the attention map from VIT ABS VIT to human attention on VQA. So for example, what color of plant is in the window, it will basically highlight the regions about the plants. And yeah, and with that, we also did experiments on like vision only tasks. For example, we trained the model on we evaluated the model on like Pascal VOC, Cityscape 8020K for segmentation, and we also evaluate the model on OD images as well. So we can see like compared to like standard like self-attention based transformer models, this top-down attention designed transformers are going to be getting like a better performance across different benchmarks. And we also show some like visualizations on ImageNet. And with that, we can see like this in this work, this top-down attention is able to adjust the feature representation based on the high-level goal and or high-level task descriptions, and we can actually enable like better generalizations on different tasks. So the next thing I would like to show you is how to use this design for better test time adaptation for new tasks without retraining the backbone from scratch. So the work I'm gonna talk about is TOAST. It's called like a top-down attention steering for large model adaptation. So again, this is the joint work with Baifeng Shi, Siyu Guy, and Trevor Darrow from Berkeley. So when you talk about like transferring like adapting like large models, like large vision models or large language models, a commonly used approach could be like a LoRa, which essentially decompose the weights for like efficient transfer, and also like visual prompt tuning. But if you look at this figure, we can see that none of these approaches actually the attention map of this approaches, it will actually focus on the object we actually care about. So often it doesn't really lead to like a better performance. So this one is actually showing like how if you have like compared to like fine-tuning method, LoRa or VPT models, so we can see the overlap of the attention map to its actual object segmentation is pretty minimal. So this is basically saying like this method doesn't really focus its attention on task relevant features. So how do we actually use like a task adaptation? How do we adapt models with like task top-down attention refocusing? So first, you can see like on this image, like before refocus, like everything is pretty random. You see like highlighted region everywhere on the image. And after refocusing, you will see like the attention map is mostly on those like foreground objects. So we found that by re-steering or refocusing the model's attention, we can actually significantly improve the downstream model performance. So the architecture is like a kind of similar to the one you just see. It's like on the first step you have this like VIT model in the feed-forward pass to generate like all the salient objects from the feature, and then like we have this like feature selection steps, and then we have the feedback pass to adjust the features of the backbone network, and then like we do another round of feed forward. So the kind of the design is similar, but now we don't really train all the parameters. We only train the orange part. So basically, we can refocus the attention by tuning the top-down attention, and then like we freeze the pre-trained backbone and only tune the top-down attention part. So the way it works is like we first have given a pre-trained transformer. We will first randomly initialize the top-down attention module and follows the two-stage tuning pipeline. The first is the pre-training stage. This is to pre-train the top-down attention on a general public dataset. For example, it could be like ImageNet for vision or open like web text for language to get a better initialization. This is because like imagine if you have a pre-trained VIT or if you have a pre-trained large language model. So the weights are already trained, and we don't have a trained like top-down pass. So we would like to have a pre-training stage to give the model some like better initialization. And then like the second stage is like tuning stage, which is to tune the top-down attention feedback pass on the new data set or like new downstream tasks. So the idea is pretty simple. So let's look at how the results look like. So again, like I would like to show you this attention map of different methods. So the first two rows are actually evaluated on the BERT classification, And this last two rows are evaluated on car classification. So we've compared like a toast with like a fine-tuning method, visual prompt tuning, and the LoRa approaches. So you can see like only the toast approaches can actually correctly attend to the foreground object region. And we also evaluate the toast method on like fine-grained classification tasks. So here across like all different benchmarks, we can see like toast even outperforms like fully fine-tuning models on fine-grained classifications. And compared to other methods, it's also working much better. And we also tested the model on like a VTab like 1K, which contains like 19 data sets of like a natural and specialized image classification, as well as like image structure understanding tasks. So each data set has like about 1K training data, and we simulate steering like transfer for low data regime. So this again is a pretty intense like a table. I don't want you to really read all the numbers, but the conclusion is Toast actually outperforms previous baselines on about like 11 out of like 18 tasks for image 1K pre-trained models, and 10 out of like 18 tasks for ImageNet 21K pre-trained models. And we also actually applied this method for like a language task as well. So it applied the Toast to Llama 7 billing and the Llama 13 billing and trained it on Alpaca dataset compared to the open source like Alpaca model, and also trained the model on like shared GPT dataset to compare with Macronia models. So for evaluation, we follow the like we use like GPT-4 as the judge to evaluate the output, the text output, to compare this like the generic knowledge, role play, common, firming, counterfact, writing, and with a score from like 1 to 10. So overall, we can see like after tuning the model with like a Toast method, it's actually outperforms like the publicly released language models as well. So some like examples, like qualitative example, like how can I improve my time management skill? And this is the reply from like Alpaca 7B. It's not bad, it's reasonable. And if you see this one is like a LoRa pre-trained model, it's kind of like similar. So it's saying like, okay, improving time management involving breaking down like tasks into smaller, more manageable chunks, etc. So this is similar. And if you look at like the Toast result, it becomes like a more detailed and informative. So it's to some degrees, it's like model is giving like a better like adaptation capability for like when you do like instruction tuning. And like one of the drawback for this type of method is like we actually have like two pathways for prediction. So you first need to go like one feed forward pass and have a feedback pass, and then you have to do a feed forward again. So it could be potentially costly. So to solve that issue, so we actually did some optimizations to reduce the tunable parameters by applying LoRa on the feedback pass to reduce the cost for feedback pass as well, feedback pass. And we also trying to do a late, like to only run the feedback on the later stage of the network to reduce the computational flaws. So again, this like a thing like with this type of technique, you can kind of like mitigate the additional cost of having additional like a feedback and feed forward loop in your prediction, and getting like a pretty competitive results. All right, to conclude, I've kind of give you like a brief like introduction about like how we design like dynamic representations for efficient learning, how we can actually build like a task-aware predictions through like a weight prediction and top-down attention. So feel free to ask me questions if you have any. Thank you.
Thank you. It's not okay. Thank you, Xin, for the talk. So now the floor is open to the audience. If any questions, please raise your hand. Yeah, then we can bring the speaker to you. Okay, it seems we don't have a direct question. Then, Xin, can I have a simple question on the? It seems I was quite caught by the results on the VQA. So it seems different queries can really directly get out the corresponding regions that is really picked up by the attention mechanism. So I just want to understand what's yours see as the limitation factor. There must be some cases that the network got puzzled, and if you ask some, let's say, prompts that needs to focus on the global area instead of a single objects, how do you see for VQA tasks this kind of dynamic attention, like interact with the diversity of the prompts that we have to face?
Yeah, that's a really good question. So actually, as you can see from the result, most of the attention is actually focused on single objects. So for example, if you talk about is Husky looking at the camera, it will actually focus on the Husky. And what if like it kind of doesn't really have the ability to reason if I want to focus my attention to camera instead of like Husky? So here is still kind of limited in a sense. It's trying to find the most relevant foreground objects instead of give a stronger like understanding or reasoning about the task description itself. So I think that's kind of a limit for the work. And in a sense, like since this work is kind of around like the vision-based models, if you imagine like in the future, if we have like a stronger multi-model model that has like both like a stronger reasoning ability from the language side and also strong like a visual side, a visual representation side. So this technique could be potentially be improved.
Yeah, it's quite exciting. I mean, if we can observe this kind of robustness, right? If we have lots of foundation models talk to each other dynamically in a robust manner, that's really, really pretty cool. Mm-hmm. Yeah, any other questions from the audience? Yeah, we do have one question.
Well, thanks for your talk. So I feel like a question about the transfer learning we talked about mentioning. So it looks like the feature selection model is a technical model to attention. So do that slow down the difference?
Raishin, did you hear the question clearly?
Can you actually repeat the question?
I can try to repeat the question if I got it correctly. So it seems the feature selection module is a sequential module within the entire inference stack. So what's the implication on the inference speed, right?
Wait, can you repeat again? Like
yeah, so basically the feature, which work this one is referring to? Okay, so for the transfer learning with top-down attention work, right? The feature selection module is kind of concatenated in a sequential manner within the network. Does it have a speed implication during inference?
Actually, yeah. So now I understand the question. So you're talking about the feature selection module. So let me move to that slide. So the feature selection is actually not really done in a sequential manner. So for example, if in the first step, you kind of like go through the entire network, you have the top layer features, and then you go through this like a feature selection model. So then like after you done that, you actually have this like feedback pass, which is basically give you a top price back to the each like layers in the bot like layers is through a linear layer. So in this way, I think the feedback pass could be an implication for speed limits, but I think the feature selection part should be relatively fast. So in our experiments, we show like if you do some like optimizations on the pathway, for example, by only applying the the feedback pass to the later stage, you can reduce the flops and training time for this like models. So for example, the fully fine-tuned model is probably like 1x, and then like the toaster method is probably like 1.5x. But with that, you can actually significantly increase the accuracy. So there's definitely a trade-off. It could be considered as like a trade-off for this method. So hopefully answer the question.
Actually, I still have a follow-up question.
Yeah, I think yeah, we're still on the time frame. So one more question, final question. Yeah.
So yeah. So you were saying actually if they put inputs, you need to like go to the last layer and then like have the signal back to the previous attention layer. Did you think something like that? So that'll be very slow.
Yeah, so the question is, if you have to reach the last layer to get the features, and then based on that information to do the pre-processing again, it seems pretty slow. So what's your thoughts on this feedback?
Seems pretty. I think okay. So I think in the worst case, you're gonna be double the prediction like in first time. So I think that's the worst case scenario, because you kind of like need to first go through the network and then like routing back to the starting point of the network. So that's bad. So you can see like in this table, we see like almost like 2x like flops in terms of like inference compared to the basic network. But I think if you just go through later stage, it will largely reduce the computational cost for this method. So I think with that, I mean, yeah, so I think theoretically it will be slower, but I will also find that because of this, like you already have in the first pass, you already have your like a computational graph like set it on the device. So actually the second pass is not that slow compared to the first pass. So that's why we didn't really experience like that delay, that much delay in the method. But that's a good question. We need to like more investigation on that.
Oh, thanks so much.
Yeah.
All right, I think yeah, that's really great discussion. We are on top of the time for this slot. Thank you, Xinrui, for the great talk. Yeah, keep in touch.
Thank
yes,
you.
so I want to quickly apologize for the technical issue we are facing here.